this video we're going to go over the heat transfer basics. So these are how to calculate heat transfer, which is denoted by Q. So heat is measured in joules and it can be calculated from the equations here or from the steam tables which you may be given. So using two methods, calculate the enthalpy required to heat 3 kilograms of water at 20 degrees Celsius to 140 degrees steam. So if we try and visualise what's happening here, we have 3 kilograms of water and we're going to take it from 20 degrees Celsius to 100 degrees Celsius. We have 100 degrees Celsius, which I'll explain later, and then 100 degrees Celsius to 140 degrees. So we have 3 stages of heat transfer here, which we're going to calculate separately and then add together at the end. So we have 20 degrees to 100 degrees. We're heating up the water and it's in liquid form here. At 100 degrees, assuming we're working at atmospheric pressure, 100 degrees is the saturation temperature. This is where the water vaporizes to vapor. It's also called the latent heat of vaporization, and it's why there's no temperature change when changing from liquid to gas, because that energy is used to vaporize the water. In the steam we have 100 degrees to 140 degrees as per the question. So you have water, gas. And we're going to use the equations and the steam table because they're the two different methods used to calculate the enthalpy, or the heat transfer, sorry. So if we use the equations, we use Q equals mCp delta T. So because we're working within a temperature range, the Cp we're going to use is an average of the temperature range. So 100 plus 20 is 120, divided by 2 is 60. So we're going to use the Cp, the specific heat capacity, at 60 degrees for this bit. So if we call this Q1, Q2, Q3, so Q1, so we have 3 kilograms, mass is for, M is for mass, times Cp, so we're given Cp of F, so F of fluid, 60 degrees is 4.185, multiplied by change in temperature, delta T, which is 80 degrees, and that comes out to 1004.4 joules, actually kilojoules if we look at the units. At 100 degrees, this is the enthalpy of vaporization, so this is this bit. So we would need the value at 100 degrees, which is 2257 kilojoules. Now Q3, we do the same here, so we have 3 kilograms, we need the average Cp, so 100 and 140, the average is 120, and we're working with gases, so it's this column. The Cp is 2.124, and then it's obviously multiplied by 40, because that's the temperature difference. So Q3 is 2.124 multiplied by 40, and then we add them all up to get Q, because all of these three things happen when we heat the water. So we have 1004.4 plus 2257 plus 254.88. So the heat transfer, or the energy transferred, is 3516 kilojoules. If we use this method where we use the average Cp and we use Q equals mc delta T. The other method is using the steam tables, which is a bit more accurate because we're not taking averages. So Method 2, steam tables. So we still have the same process in that we have 20 to 100, 100, 100 to 40. So if I write that again, 20, so we have water here, liquid, water, steam, and then this is the vaporization part. So we're going to minus the enthalpies. So to find out the enthalpy difference, so 100 degrees here, so 4192 minus the enthalpy of 20, which is 83.90, and that will give us Q1, because we're just calculating the enthalpy difference. So that is 335.3, and that's kilojoules. But remember that we have to multiply by 3 because we have 3 kilograms of water, so we can do that at the end, but we need to make sure not to forget it. So we're at 100 degrees, the enthalpy is 2257, just like before. So 2257 kilojoules per kilogram. Sorry, one thing I've just remembered, on the previous one, I forgot to multiply this by 3, because this is per kilogram. I multiplied them by 3 on here and here, but I'm mistaken to do it on here. So the actual answer for this bit will be 1000 is 4 plus 0.4 plus 254.88 plus 3 multiplied by this. I apologise. It's quite a common mistake, but it's a very bad one. 8030.28 kilojoules is the final answer. So always remember that if when we look at the unit as per kilogram or specific, and it's multiplied by how many kilograms of the substance you have. So if we look back here, per kilogram, so we do the same for 100 degrees in steam, so 140 degrees of steam is 2734 minus 100 degrees in steam, which is 2676. 2734 minus 2676, and that gives us 58. So now that we've got that, we can add all of these together and then multiply by 3. So the Q equals 3 multiplied by 335.3 plus 2257 plus 57. 2650.3 multiplied by 3 gives you 7950.9. That's in kilojoules. So if we compare these two values, thankfully I spotted the mistake, or else 3000 would have been quite far off. They're meant to be quite similar, and they're both used because you get roughly the same results. It depends on how accurate you want them. So these are roughly around 8000 kilojoules, but I would say that the steam table one is more accurate because you're not taking averages, and the values on the steam table are more precise and accurate to the real value because they've been doing experiments to get those values. And that's it. That's how you calculate the heat transfer.